Welcome all to Constant Rate of Change lesson for today. Let's go ahead and pause, take a look at your answers, come back when you're ready. I have numerous pages for this. I chose not to put an answer for C. We'll see what you say. Here is a graph that goes with a scale of 25s and 10s. The next graph, this is a scale going by 20s and 10s. You'll see slightly different, I guess you could say, steepness of the lines. Last page. And here we go, folks. For today, the focus is finding a constant rate of change from a table or a graph. That's going to sound and look awfully familiar to what we've been doing. So let's just first start with our definition, shall we? A rate of change is a rate that describes how one quantity changes in relation compared to another quantity. So, rate of change is often expressed as unit rates. But let's talk about a constant rate of change. This makes a linear relationship. So when you look at a graph, it'd be a straight line, not a curve. The rate of change between any two quantities is always the same. Now that's going to sound like proportionality, but there's some subtle differences. I want you to think about this. I'm going to draw an analogy to squares and rectangles and quadrilaterals. Now I want you to consider this phrase: every square is a rectangle, but not every rectangle is a square. Now think about that. Every square is a rectangle. It's got 4 sides, 4 right angles. But not every rectangle is a square. So in other words, squares are special rectangles, right? Another relationship to think about: every rectangle is a quadrilateral, but not every quadrilateral is a rectangle. In other words, rectangles are special quadrilaterals that with 4 right angles. But if you look at the yellow shapes, there are parallelograms, trapezoids, and other quadrilaterals that are not rectangles. So again, think about that. Every rectangle is a quadrilateral, but not every quadrilateral is a rectangle. Now, in like manner, I want you to consider this, and I'm just going to plant the seed and watch it grow. Every proportional relationship will have a constant rate of change, but not every relationship with a constant rate of change is going to be proportional. We've seen that occasionally in the last week or two, but I'm going to keep talking about that as time passes. Now let's talk about some examples with tables. Computer programmer charges customers per line of written code. Fill in the blanks with the amount of change between consecutive numbers. Now I find this really interesting. First things first, you guys know me, I often will go ahead and label the table to show that the cost depends on the lines of code, right? Now in this case, the cost first increases $1,000 for 50 lines of code. In the next case, from 2000 to 3, well, there's another $1,000 for another 50 lines of code. And then we have, oh, well, look at that. It's always $1,000 for every 50 lines of code. Now, in labeling the diagram, and sorry, folks, if I didn't say this before, this is in your notes. We have to identify first that the change in money depends on the change in lines. That's why we put dollars per line. And then we find the constant rate of change by basically reducing it down to a unit rate. So in this case, there is a constant rate of change. How much is that? Sure, you could say $1,000 for every 50 lines, but it's a lot more communicative, or maybe I should say a lot clearer, to say $20 per line. Example of this that I don't think is in your notes, so just bear with me. I had a video for this. But again, look, even for a table that goes vertically, we establish a relationship where there is $40 increase for every 5 cars washed. Now, when we write that, we make sure to describe dollars per car because the dollars depends on the cars. And then we rewrite it as a unit rate. So in this case, $8 per car is the constant rate of change. Yes, I know that this is going to sound very familiar. Whoops, that's not what I wanted to do. I just wanted to go to the next page. There we go. All right, now let's talk a couple examples that are in your notes. First things first, I'm going to look at the distance. Then I'm going to look at the time, and of course distance depends on time, so I'm going to remember that. In fact, maybe even before I do this, I'm going to go ahead and write my ratio as miles per minute. Now it looks to me like the miles here increases by 90. as the minutes increases by 30. Let's check the next relationship. Increasing another 90, increasing another 30. And let's check the last. Okay, there we go. Increases another, wake up, Mr. Callan, that would not be 90, would it? That would be 290. And another 290 for every 30. So if we were to establish a ratio of 290 miles increased for every 30 minutes driven, we could then go ahead and, a little magic pen here, reduce by 10. It'll make it a lot easier on you. But I'm going to go ahead and I'm going to simplify that down to a unit rate. And let's go ahead and leave it as a mixed number. 9 2/3 mile each and every minute. That would be the constant rate of change. Let's go ahead down here and compare the number of students per bus. Again, the students depends on how many buses there are. And if I look here, I can see there is very clearly a rate. Now, be careful, because just because one of them is okay does not mean both of them are. But when I look down here, I see an increase of 72 students, another increase of 72 students, and another increase of 72 students. Now, again, what I like to do is I like to write the units first to make sure I don't write 1 every 72. I write 72 every 1. In other words, 72 students per bus, which is an awfully big bus, huh? Now let's talk graphs, shall we? And forgive me that my graphs look a little tidier than yours. It's nice to have that color in here. But if you see, every time there appears to be an increase of 60 miles for every, now notice I'm not counting tick marks. I like to look per 1 hour. Another 60 miles for another 1 hour, and another 60 miles for another 1 hour. And therefore, we can find that constant rate of change, 60 miles per hour. And that would be our unit rate. Therefore, if I look at the points, the point 0, 0 is going to represent 0 hours and 0 miles. The point 160 is going to represent 1 hour, 60 miles traveled. Notice that that is the unit rate. Interesting. Let's carry on with the next example. Now, this example you will find in your textbook, or in your notes, excuse me. And a little harder to see because it goes right in between the tick marks. But when it's difficult to see, almost always they will produce for you the ordered pairs. So notice here that we can go up 30 miles for 1 hour, and we can go up another 30 miles for the next hour. And yes, we do find a constant rate of change because the rate of change doesn't change at all. Every time it appears to be, I'm going to go ahead, you know me, miles per hour. So there is our unit rate. Again, let's examine the point 0, 0, and 130. What does 0, 0 mean? Well, 0 miles driven after 0 hours. What about the second one? I almost always start with what we're measuring. So what does that 30 mean? Well, 30 is the y-axis. 30 is the y-coordinate. And therefore, we're talking about traveling 30 miles. 30 miles were driven, huh? After 0 hours. This example, not in your notes, but just another example of how you can see on a graph an increasing trend. It appears to be going up 8 every 1. Let's check it again. From 8 to 16 is another 8 every 1. So super cycle, $8 per hour. Now I want you to look at the table. In the table's case, we have a different relationship for pedals rentals. And here we have, let's try that again. Oh well. In this case, we have $12 every hour. Now, what we're asked to do is to find which store charges more per bicycle hour. And so, as you can see, Pedals Rentals charges more. Why? Because we're talking about $12 per hour compared with $8 per hour. So that's how you can compare two constant rates of change, even if they're represented differently, if one's a graph and the other's a table. All right, let's wrap it up with your last example and notes. The table and the graph below show the amount of money Mealing and Daniel save each week. Who saves more each week, and explain. All right, first things first, I'm going to examine Mealing. I'm going to look here and ask, okay, does it in fact have a constant rate of change? The first change is $15 for 1 week. The next change is $15 for another week. So Mealing does have a constant rate of change, $15 per week. Then we're going to go ahead and look at Daniel. Daniel appears to go up $10 for 1 week, up $10 for 1 week, up $10 for 1 week. So just like Mealing has a constant rate of change, so too does Daniel. The question was asking us to compare who saves more each week, and in this case, it's going to be Mealing. Now, I'm sure you can write a more convincing argument than that. You would say something about, while Mealing saves more each week. Mealing saves $15 per week, which is $5 more than Daniel's amount, something like that. Pause if you want. Write down what the next point means, the next 2 points. Now, in this case, 0, 0 represents $0, 0 weeks. What does that mean? Okay, that means that Daniel starts, and by the way, I shouldn't have said exercise 1. I should have just said the graph. Daniel starts with, bingo, no money. Point 110 represents $10 were saved after 1 week. Then I want to leave you with how can you find the unit rate on a graph as long as it goes through the origin? So I want you to pause, think about that, come back. As long as it goes through the origin, folks, if you have a comparison of anything to 1, that is the point that you're looking for. And so in this case, look for that first point. As long as it goes through the origin, look for that first point on the graph, and you will be all set. That's what I have, ladies and gents. Assignment number 10 coming at you. Do well, and let's grow.